This is pre-calculus, notes 8.1. This is video 6 of 6. Find the value of x in each of the logarithmic equations by writing the equation as an exponential equation. Leave your answer in exact form when possible. Otherwise, round your answer to 3 decimal places. So here's the key that tells you you should probably put this in exponential form, because the directions aren't going to always tell you that. Whenever you have a logarithm equal to a number, and the variable for the problem, let's just leave it at that. Whenever you have a logarithm equal to a number, it's likely you're going to want to change this to an exponential equation. So looking at number 1, as an exponential equation, it would be the base to the exponent equals the argument. Great, x is by itself. But do we have a good idea what x is? Well, using our exponent rules, we can change this exponent to be positive by reciprocating the base. So I can make this 1/9, and then that changes the exponent to a positive 2/3. So we could leave the answer like this. It's hard to know when to stop. It says leave the answer in exact form. So we can do a little bit more. Do we know what the cubed root of 9 is? We don't. Could we square 9 and could we square 1? We could. So we could make this 1 squared over 9 squared. We essentially took the squared part of this and put it on the top and bottom of our fraction, and we left the cube to 1/3 on the outside. 1 squared is 1, 9 squared is 81. Now it's the third root of x, which you could leave it like that, or you could write it as the cubed root of 1 over 81. So in this particular problem, you could have lots of these things be the answer. I would say any of these would work. Some of these we definitely want to have a better idea of what x is. Like in the second one, let's see what we can do here. If we change this to exponential form, right now it's in log form. The base here for this natural log is an e. So it's the base raised to the exponent equals the argument. Well, now it's just an algebra problem. We're going to add 1 to both sides. Whoops, didn't add it to the left. I'm going to divide each term by 2 or multiply each term by 1/2. I'm just going to multiply each side by 1/2 and write it like this. This is one version of the answer. An exact answer. If you wanted a rounded answer, you would use your calculator. Number 3, this is also natural log, so the base is e. E to the exponent equals the argument. Once you get it in log form, getting x by itself is easy. We just subtract 3 from both sides. I want to add something here to the notes to make this a little more clear. This is in log form, and this is in exponential form. You might look at this later and be like, I don't understand what happened. We just changed the form that it was in. That's the first thing that we looked at in the first video for the notes for this section. So we're going to be continuing to do that for each of these, because when you have a logarithm equal to a number that doesn't have a logarithm in it, you're likely going to want to do this. So number 4, this is the base of 3 raised to the exponent equals the argument. Now 3 to the negative 3 would be 1 over 27, because 3 to the third is 27. This negative says we reciprocate it, we get 1/27. Then we could, there's lots of things we could do. I want to get rid of my fraction here to make this simpler math. I'm going to multiply every term by 27. That would give me 1 equals 54x plus 27. Then I'm going to subtract 27 from both sides. Then I'm going to divide each side by 54. I'm going to reduce my fraction. by dividing the top and the bottom by 2. So x is negative 13/27. Number 5, this is currently in log form. Let's write an exponential form. We have the base raised to the exponent equals the argument. Now, one of the things that we learned in the exponential function chapter is that if we're trying to solve for this exponent, we need the base on the left and the right to be the same. Now, this base of 25, I could write as 5 squared, and it's already raised to an exponent. Power to a power property, you multiply the exponent, so this is 5 equals 2 to the x. On the right, this is 5 to the first times 5 to the half. The product property, when you're multiplying with the same base, you add the exponents. 1 plus a half would be like 2 over 2 plus a half. Getting common denominators, that's 3 over 2. One of the identities that we had, property of equality, I believe was what it was called, for exponents, is if you have one expression on each side of the equation and they have the same base, you can set the exponents equal to each other. So therefore, 2x is equal to 3 over 2. We multiply both sides by a half to get rid of the times 2 on the left. We're going to get 3 over 4. Multiply both sides by a half. When you multiply fractions, you multiply the tops, you multiply the bottoms. Next one, I'm actually going to do this one a little bit differently. Instead of making it, if I change this to exponential form, you don't need to write this down. If I change it to exponential form, I'm going to get 2 to the x plus 2 equals 9, which is all fine and good, but we can't do what we did on this last one. This last one, we got the same base on both sides. There's no way for us using integers to get 2 and 9 to have the same base. So that is not going to work out well for us. So let me get rid of the fact that I said I was going to do that. I'm going to use the change of base formula. On the left, I'm going to use a common log base. So I'm going to change this to common log of 9 over common log of 2. The reason that we don't have to do anything else with the left is because getting x by itself is super easy. We just had to subtract 2 from both sides. So we got common log of 9 over common log of 2 minus 2 equals x. And that's it. It said exact answer is when possible. It was possible for all of them. That concludes 8.1 notes. Please do the homework assignment that accompanies this.